Space weather is something that Earth experiences every day, and it happens because we live near a star. Out in the countryside near Boston, Massachusetts, scientists at MIT's Haystack Observatory work to understand what happens to Earth's ionosphere and our technology when the sun stirs up a little space weather.
One of the ways that we learn about space weather is to measure its effects on the ionosphere, the region of charged particles at the top of our atmosphere. We can do this with our radar systems, but there's another way, with radio signals from Global Positioning System satellites, GPS. GPS provides timing and navigation services for airplanes and ships, trains and delivery trucks, cellular phones, and even our banking system. The satellites provide time code based on their internal atomic clocks. GPS ground receivers also have internal clocks, and they compare their own time with the time code from each satellite they see. They can calculate distance by taking the speed of the signal they receive and multiplying it by the time it took to travel that distance. Each receiver sees multiple satellites, which allows it to calculate its position very, very accurately. Dr. Anthea Koster is one of my colleagues here at Haystack Observatory. While I study ionospheric changes using our big radar systems, Anthea does the same thing using GPS technology. She is very interested in what happens as GPS signals pass through the ionosphere, particularly during space weather events. I recently sat down to talk with her about her research. So Anthea, why is space weather so important when we're talking about GPS signals?
Well, one of the reasons is GPS is a satellite system, and like all satellite systems that use radio wave communication, space weather affects their signal reception. And the reason for that is that they have to be able to detect their signal from the background noise. Now, GPS signals are relatively weak to begin with, and during some very large solar flares, the background noise level on the sunlit side of the Earth can be raised quite dramatically, especially in the L-band frequency range where GPS operates. When this happens, GPS receivers have a hard time picking out their signal in the background noise environment, and GPS receivers have been known to lose lock on multiple satellites at the same time. And when this happens, it can impact your navigation and timing.
During space weather events, our big radars often detect very large changes in the ionosphere which affect communication systems. Does GPS have problems as well during these periods?
Yes, and that actually brings us to other impacts that space weather has on GPS. One of these effects, which happens when the ionosphere is changing very, very rapidly, is called scintillation. And when the ionosphere is scintillating, GPS can lose lock on several satellites at the same time. Another important fact has to do with the relation that you mentioned earlier, and that is that the distance is actually a function of the time that between when a signal left the satellite and when it's received by the receiver, times the speed of light. But actually, it's not traveling. The radio wave is not traveling through the ionosphere at the speed of light. It's slowed down by the ionosphere, and we have to take that into account. In periods of low or no space weather, the travel speed isn't really affected very much, or if it is, we know how to account for it. But in very large space weather events, it can be affected quite a lot, especially in one direction and not another direction. So if space weather is occurring and we have the situation where in some directions we have a lot of effect on our speed and in other directions we don't have very much, receivers can get confused and it can affect their positioning information.
So the errors you mentioned could be quite significant, especially for the technology that we use that depends on GPS.
Correct, and people need to be aware of space weather events because during those time periods, GPS may not be quite as accurate as it normally is. There are examples of people who really need very, very accurate positioning information. For example, airline pilots pilots when they're trying to land a plane. They really need to know their vertical distance to about 10 meters. Now, the FAA designed the Wide Area Augmentation System to take this into account, and they're aware of when space weather events are happening, and they warn the pilots not to rely on GPS during these time periods. But there are other examples of people who really need precise positioning information. For example, barges going in inland coastal waterways need to know their horizontal accuracy to about 5 meters. They're not going to have that during space weather events. Oil platforms out in the Gulf of Mexico really need to know their positioning accuracy. And trains coming into stations. A bit closer to home, your GPS unit might give you the wrong information about your location. It might impact your cell phone reception, and it could halt your financial transactions. GPS is embedded throughout our technological society, and because of this, we really need to be aware of what effects space weather has on GPS. And that's really something that we're working on today.
So as you can see, space weather is more than just something that concerns scientists. It's a phenomenon that affects people and the technology we use in many different ways.